with less older buildings and less students. But so I am very happy to be there again in front of, I hope, as good students as last year's, I'm sure. And so this course is about quantum field theory 2. So it's an advanced course, more advanced course on what you did last week or last month. And I think the purpose of this course is to introduce you basically to the method of path integral and functional integral, so quantization by summing over all possible classical configuration of quantum systems when it's possible to define a classical system. And it's a very important and complementary both formulation and picture of what a quantum system is. And so this will be basically the first part of the course. So the first part of the course, basically this week, is going to be about path integrals, methods in quantum mechanics and in quantum field theory. So I'm going to, in some sense, reformulate what you have seen in QFT1 and possibly some of the other courses via canonical quantization using let's say the canonical or traditional formulation of quantum mechanics in terms of Hilbert space and operators and Hamiltonians in terms of path integral. The second part, which is going to be the second week, is to discuss, mainly from this point of view, but its application, renormalization theory. So, which is one of the very important and essential features of quantum field theory. That makes a difference between quantum field theory and simple quantum mechanical non-relativistic system. And I think you heard already a bit about the need for renormalization in QFT1 if you have discussed some one-loop diagram, something like that. So I'm going to make a more precise presentation, not complete, but presentation of what the problems are and what is the standard solution, which is renormalization theory, to define quantum field theory in a consistent way. This is also going to make a connection with renormalization theory in condensed matter or statistical physics. I think that you had an introduction to that in the statistical mechanics course, in the relation with critical phenomena. So I hope that you have a clear picture of why the idea of renormalization in condensed matter and statistical physics is some, the tail, and this is the head of the same physical problem and mathematical theory. Okay. And the third week, if I'm going fast enough, as I hope, is devoted to applying this method to theory of, well, some simple theory of real use in high-energy physics, namely path integral method and renormalization both for fermions, or Dirac field, if you want, and gauge series, both abelian, namely QED, and non-abelian, namely Yang-Mills theory. So I'm not in a position, I won't have time to do high energy physics. I won't discuss. You are going to see that, I hope, in next lectures. But the high energy information. Okay. So I think you might have already the lecture note I left from last time, I think. Yeah. So I'm going to follow that, but also I'm flexible. I hope so. So don't hesitate if you have questions. Either, well, you're welcome to ask questions during the course, of course. It's the purpose of having a real physical lecture in front of you. And also, don't hesitate to send me a mail, just show show in my office. I'll be there most of the afternoon. It's just in front of Debbie's office, or send me a mail or whatever, or we can discuss at lunch or dinner, because I'll be staying there for the 3 weeks. So please ask questions, make comments. Okay. Okay, so let's start with path integral. So I think well, Dan told me he gave a short introduction on path integrals. So if I'm going too slowly, or too fast, just tell me. So, and also you had, I think, a good introduction to classical mechanics by David, I think. So you are supposed to be familiar, or very familiar with what a Lagrangian is, what an Hamiltonian is in classical physics, because that's important. Okay. So I'm going to start with the classical system. So I'm going to treat path integral for a very simple system, which is the archetype of the system. I'm going to consider a one-dimensional particle. Well, a particle. So a particle in one dimension with a mass m and in a potential v. So the position, so the particle lives on a line. Its position is q. This is space. I'm going to denote the position q. So a trajectory is denoted by a function q of t. And for this system, the Lagrangian function is just m over 2 q dot squared minus v of q. This is the Lagrangian. And out of the Lagrangian, you derive the Lagrange equation so the equation of motion, and the corresponding Hamiltonian is h equal p squared over 2m plus v of q, where p is a conjugate momentum to the position. So p is mq dot. Of course, dot is a time derivative. And so this is m dq over dt. And the Newton equation or the Hamilton equation are derived from those two quantities. Okay. So now this is a classical theory, and we are interested in the very classical problem of quantizing this system. So we have to define things now for the quantum theory. The state space of the system is described in Hilbert space. So, and we have states which are defined by. So the Hilbert space is just basically the space of L2 function on the real line, basically, more or less. I won't be very mathematically precise, but I think you have seen some more precise definition in the quantum mechanics core course. I can give them, of course, but so basically one way to represent state is in terms of position states. So you have a basis, well, it's not exactly a basis of position eigenstate, which I'm going to denote by Q, which means that you have a position, a quantum mechanical particle localized at a given time at a given position. So its wave function is something like a delta function at Q. And you have, of course, a position operator Q, which is such that Q times Q is the position of the particles, q times q. That's the definition. And of course, this position eigenstates satisfies the scalar product. That the scalar product is the delta function of q minus q prime. So they are not normalizable states, but that's enough. This rules is enough. And of course, there is another basis which is given by momentum eigenstates, but I'm not going to discuss that at that stage. And this is just a very standard quantum mechanics. And out of this basis, a general state for the systems, an element of the quantum system, are going to denote it by in this bracket notation of Dirac by psi. And to this general state, that's an element, more or less, of the Hilbert space. And to a general state is associated in this position representation a wave function. Which is just the scalar product of psi with the position eigenstate q. And this is going to be, of course, the value of the wave function representing the state psi at the position q. So wave functions are, in some sense, element of a general state in the basis of the position eigenstate. Okay? And now you have also the momentum operator. T, which is basically given by h bar, which in this representation is given by a derivative of with respect to q. And now, corresponding to these dynamics, there is an Hamiltonian operator. Hamiltonian operator, capital H. So I'm going to use the same notation for classical quantities and operator when there is no ambiguity. But if you have doubts, just ask me. The Hamiltonian operator that describes the evolution of the systems is, of course, p squared over 2m plus v of q, where v is a function of q, and you consider here the similar functions of the operator v of q. So it's an operator that is commutes with q, which is such that, for instance, v of q, when you apply it to q, is v of the number q times q. Or if you prefer, think of v as a polynomial, for instance. V is its polynomial. This is just a corresponding polynomial of operators, which has a well-defined algebraic definition. Okay? So the Hamiltonian operator that describes the evolution of the system is given by this formula. This is just rules of correspondence, canonical quantization out of this classical system. And then, of course, the evolution is given by Schrödinger equation. So this defines the dynamical evolution. Okay. And the dynamical evolution, of course, is given by the Schrödinger equation. So the Schrödinger equation is defined in this, for acting on the wave function, as I h bar d over dt of psi of q and of t is h applied to psi of q and t. Okay? Or this is the Schrödinger equation, and in terms of states, If I consider that the potential V is independent of time, but this can be, of course, generalized to a potential which is dependent of time, then the system doesn't have a constant energy. The evolution, the time evolution, can be formulated in terms of an object which is called the evolution operator. And I think you have seen that many times, especially in the quantum mechanics course. So you have the evolution operator, which is unitary, because it conserves probabilities, and which is defined by basically, if you start at time t initial, or let's call it time t1, the system is in state psi1, which is initial. Then under evolution at time t2, the system is in state psi2. Of course, psi2 depends on t. And basically, psi2, the state psi2, is the result of applying this evolution operator to the state psi1. Because evolution is a unitary transformation, and u of t2 minus t1 is just, you integrate this. This is exponential of t2 minus t1 divided by I h bar times the Hamiltonian. So it's the exponential of a phase factor times the Hamiltonian. And think about the exponential of an Hamiltonian either as defined as the series, the infinite series that defines the Hamiltonian. This definition would be precise if the Hamiltonian would be bounded, but the Hamiltonian is not bounded in general, so this requires a bit of math to make sense out of it. But I think you have seen this math in the quantum mechanics course, because I think at the end you heard about what are called ridged or Hilbert space. And so there is a mathematical theory that is out of that. And of course, since this is independent of time, this is t2 minus t1 times h. So you see it depends only on t2 minus t1. So often I'm going to I express that u depends only on t2 minus t1, and that's because of time translation invariance. If the Hamiltonian was depending of time, then the evolution operator is defined, but it depends on t2 and t1, but not the difference, because there's no time invariance. Okay? So this is the definition of the evolution operator. And of course, the Schrödinger equation translates into an equation for the evolution operator itself. Good. So I think that's all what I need. And then, so this is, in fact, the standard formulation of quantum mechanics in what is called the Schrödinger picture. This is a choice, for instance, this choice of basis for the states where when there is no evolution, well, basically the basis is the same at different time. Okay. So this means that in this Schrödinger picture, states evolves with time, so it depends on time, and operators, let's call them A, operators that correspond to observables in quantum physics do not depend on time. And of course, in quantum mechanics, everything amounts to computing, the probability to get some results for a measurement operation on a given state. And I think you had in the quantum mechanics course, as far as I've seen on the videos, an extensive discussion already of all the subtleties of what is a quantum mechanics and why the quantum formalism that was devised now more than 80 years ago is a fully consistent and mathematically meaningful formalism, despite its seemingly paradox. But basically, the expectation value so let's say of an observable A on a given state psi is given by the scalar products of psi with the operator. It's non-normalizable state A dot psi. So this is famous. This is Born rules. So basically, this is the consequence of Born rules. Okay. And so in this state, in this formulation, you see the operator depends on time. The operator, a priori, if you do not change your apparatus of measurement with time, then A doesn't depend on time, and this is the expectation value of A on a state psi at a given time t. So this depends on time through the fact that psi depends on time. Okay. So now you have another picture that I think you have seen already. How is this working? Which is the Heisenberg picture. And in the Heisenberg picture, basically, you rotate your basis, for instance, your position basis for the quantum states, the basis, so that the matrix element, namely the value of the function, rotate according to psi. And in this Heisenberg picture, the states basically do not depend on time, it's just a representation. And the operators depends on time. It's just a change of basis. So of course, no physical quantities, no quantum probability, no quantum expectation value, no quantum probability will depend on this picture you choose. And you obtain this by stating now that if you have a state, the states depend on time t. So if at time, let's say, if at time t equals 0, my quantum state is defined by a wave vector psi, then at time t, what I call psi of t is just the initial state while I absorb the evolution by its conjugate, or its inverse. Remember, since u is unitary, u of t, u dagger of t is u minus 1 of t. So this is the inverse, but this is also the hermetic conjugate. So you see that with this definition, this is for a given time t, but what I mean that the states do not depend on time, it means simply that under evolution, psi of t in the Schrödinger picture is the same state that the initial state psi of 0 at time 0. That's what I mean. So the matrix element of psi. But, of course, in order to keep this formula for the expectation value, an operator which is described by A, an observable, which is described by an operator A at time t, has to be described at time t equals 0, but at time t, the corresponding operator is described by u minus 1 of t, a u of t. So that yes, so that this, you get the same formula for this in the Schrödinger picture and in the Heisenberg picture. Okay. So I'm mentioning this because, as we shall see, when formulating the path integrals, at first path integrals are best formulated in the Schrödinger picture, but when we go to quantum field theory and some more advanced stuff in quantum mechanics, things are better formulated in the Heisenberg picture. Just to give. Okay. Good. Okay. Okay, so now path integrals.
Question.
Yes?
I was wondering why it's an U inverse of T and say no U of T in
here. In fact, I might have made the usual mistakes of mistakenly taken. So let me check my notes. What?
A line.
Yeah?
At times you get extra line. So I was expecting the U of T gets side.
You don't understand this line?
Like why is it U inverse?
Pardon?
And you have U inverse of T.
This is U inverse, because then psi of t at time t is U minus 1 of t of U of t of psi 0. So I think it's okay. Well, let me check in my... Okay. And with this notation, psi t of t times a of t, with this notation, psi t at time t times p capital P times a of t times psi of t at time t is the same thing as psi of 0 u minus 1 of t times a times u of t times psi of 0, which is expectation value psi at time t. So it means that all physical quantities, all numbers, are the same in the two pictures. Okay. I made no mistake. Okay? I think you should check with the notes you had in quantum mechanics, but it's exactly the same thing. It's just a change of basis. And in fact, if you are still a bit puzzled by that, there is nothing really quantum in this change of picture, because in classical physics, there is a similar, you can perform the same trick, describing a classical state in Hamiltonian dynamics by either considering your coordinate in the phase space as evolving with time, or not evolving with time. So performing what's called the canonical transformation in time. So in fact, there is an exact analog in classical mechanics. So there is nothing really deeply quantum in this change of picture.
Excuse me?
Yes?
But what is the difference between psi of t and psi of t and t? Like you have
Okay.
the line at time t and under revolution then.
No, what I mean is that if I consider, basically, if this time, this is the time, well, perhaps I should have added subscript. So this is a vector in the Schrödinger picture.
Yeah.
Okay. And this is a corresponding vector in the Heisenberg picture. So those are two different vectors in the same Hilbert space.
This is okay, but then in the next line, psi of
Okay,
t.
so then in the same line, it means that if you are asked what is in the Heisenberg picture, the vector in Hilbert space that describes the state psi of t, so the wave function psi of t at time t, this is the same as the vector in Hilbert space that describes the initial state at time 0. So this is the relation between the vector that represents a given state in the Heisenberg picture and the vector that represents a given state in the Schrödinger picture. And this is an identity between the vector that represents in the Heisenberg picture two different quantum states. The state, the initial state at the initial time, and let's say the final state at the final time. So they are described by the same vector in the Hilbert space in the Heisenberg picture. And that's not inconsistent with the fact that there is a time evolution, because the operators that represent the operator in the Heisenberg picture that represent the operation of measurement of the observable A at a given time t is not the same that the operator that represents the measurement operation of the observable A at time 0. You see? So you must, in some sense, think that operator represents measurement operation in observable. Well, in simple measurement, the pure projection measurement operator. It's slightly different for more general measurement, but there is the same. Yes?
And in the last line, the
Yes.
first term is Heisenberg or Schrödinger?
So this is Heisenberg.
That means the state is not time dependent.
No, this means that when you measure this is a number. This is a result of the observation. So this is, if you want, this is Schrödinger.
Yes, but in the Heisenberg thing, so the states are not time dependent. And
No, because they are not time dependent, because we have
Okay.
this identity.
And the operator is time dependent.
But the operator is time dependent.
So if we substitute in the expression for the Heisenberg picture the second last line,
Yes?
then we get the operator A, the second last line. Then we get the operator A in the Schrödinger picture, and it gives us UT times the states in the Heisenberg picture, which is inconsistent with
No, I don't think it is consistent, because here I am representing the state that has evolved from time 0 to time t. So it's not inconsistent. Check. You see? If you want to make this a bit more precise, this is the same thing as, okay, so psi of tt in the Heisenberg picture is the same time as psi of 0 at time 0 in the Heisenberg picture. But psi of 0 at time 0 in the Heisenberg picture is the same thing as the initial state psi, initial state in the Schrödinger picture. Okay, so, and A of t is given by that. So this is the same thing as psi initial in the Heisenberg picture times u of t of u minus 1 of t times A times u of t times psi initial.
Yes, that's what I'm saying.
Okay, in the Schrödinger and in the Schrödinger.
No, in the Heisenberg.
No, because
Yes, but
this is the same as psi initial. Here, this is the formula between vectors in the
yes,
Hilbert
okay,
space.
let's take it Schrödinger. So that means that the Schrödinger state at time t is ut.
Yeah, so this is Schrödinger state as psi t. So this
Yes.
is the same thing as A. Schrödinger state at time t. So this is Schrödinger. And here we have the conjugate, so we have psi of t, Schrödinger. And this is the operator that is independent of time, that is associated to a projective measurement of the observable A at time t, at any time. So this is the expectation value of psi on the state psi at time t in the Schrödinger picture. And that's the same thing that initial state times A of t times initial state. And the initial state represents the quantum states at any time as long as you follow the unitary evolution given by the Hamiltonian age. So everything is consistent. I agree. You have to get a bit used to that, but as I told you, everything is consistent, and basically this is just a change of system of, if you want, this is a change of system of coordinates, of basis that describes in the Hilbert space. So the same thing occurs in classical mechanics. You have so it's just there is not much physics in that. It's just a change of coordinate system, a change of basis to represent your object. Because it's only these quantities that are physical.
What confused me was that you wrote the Heisenberg state with t and the Schrödinger without t, but yes. Okay.
Yeah. No, I know it's a bit
Okay.
it's a bit confusing because this represents the state,
Okay. Yes.
a state at time t. So this is a vector in time t in the Heisenberg picture. No, I agree. You have just to have used to it. Okay. But I think for now on we go back to this standard Schrödinger picture. Okay. So we start from an Hamiltonian. So we have this particle. It is given by this Hamiltonian. So we have this, let's call it method. So you have our system. We have position q. So position lives in some potential v of q. And it is described by a wave packet that evolves, and in such a particle it will bounce back, but disperse, and if the potential is bounded above, then you may have plane waves that evolve, etc., etc. And we are interested into the matrix element of the evolution operator u of t in the position basis. Okay? And so, in the Schrödinger picture, we are interested in what is, if we start from an initial state that is called Q initial. What is my notation? Yeah. Q initial. And I consider it evolves between the initial time and the final time, and then I take the scalar products with Q, another state Q final, and this is in Schrödinger picture. Okay? Schrödinger pictures. So this is a matrix element of the evolution operator. And in the corresponding Heisenberg picture, this would be QF at time TF times Q initial at time T initial in the Heisenberg picture. But that's, I'm going to consider this object. Okay. And so, you see, this is a probability amplitude, because Q of F, well, this is just the states that result from the evolution at time Tf of the state that was a position eigenstate at time Q initial. So this is basically, if I write here time, here I write the position Q, here this is my initial time, and this is my final time. You assume that you have a particle localized at the position Qi at time initial, and it will evolve, of course, it will evolve like by some wave packets. And at time Tf, I want to estimate what is the probability amplitude to evolve from Qi to Qf during time Tf, starting from this initial state, which is localized here. So this is a probability amplitude. It's a complex number. It's not probability. It's not a real number. The corresponding probability starting by being localized here at time t initial for the particles to be observed or measured being at position qf at time 2f will be the square norm of that according to Born's rule. Okay. So this is a probability amplitude. Okay. And so you have seen that, and I'm going to rederive this quickly. The path, so the path integral method, which was devised by Feynman at the end of the 40s, but there were some hints of that by Dirac and possibly by Majorana before, but the proper and good formulation of that is due to Feynman, of course, is that this probability amplitude, this number, can be written as a path integral, namely an integral over all possible classical trajectory that I'm going dq of time s, let's say. So let me call s the time to make a difference between the initial and final configuration of a phase factor which is exponential of I over h bar times the classical action which was thought for this particular trajectory. So we sum over classical over histories such that q of s, such that at initial time this is q initial, and at final time this is qf. But otherwise, trajectory can be anything up to some in some space of function. Okay, and these are not classical trajectories because they sum, and this is the action. While the action is just the integral from initial time to final time of ds of the Lagrangian. So m over 2 q dot of s squared minus v of qs. Okay, this is the classical action for history. Okay, and we have to assume that the function is smooth enough so that this object is in probability well defined. Okay. So this is the formula that you have seen. And if everyone understands that, I can go on, but I can also remind what's, well, I think that's better because I can remind a bit what is the derivation of that. Oh, this was so the basic idea is the derivation of that which is due to Feynman consists in using the superposition principle by separating this initial and final time. So, well, let me take t initial to be 0 and t final to be t for simplicity. And to, instead of computing this probability, to compute this probability as a product of small probability amplitudes for small time interval. And in my notation, the time intervals are noted, let's say, epsilon. Epsilon is a time interval, so that we have, so this is time initial, and this is time final. Time final, so that we have discrete times that I'm going to call Ti, which is I times epsilon, with I going from 0 to n, where n is t divided by epsilon. And let's assume that t divided by epsilon is an integer. Okay, so we have discrete times. And so we have the Q0, which is the initial time, the initial, and Qn, which is Q final. And basically, you write U of T final, T initial, as a product of U of epsilon to the power n, because it's a product of n times evolution operator for a time interval epsilon. And you use the fact that at each time interval, you may insert a decomposition of unity by writing the fact that 1 is integral over dqi times qi. So you insert unity between each point, so that you write this matrix element, Q final, U of T, Q initial, as a product of n matrix element of the form. So you have a product of dq1 up to dqn. And then you have a series of product of matrix element where you start from Q0, you have U of epsilon Q1, and then you go up to the n where you have Qn, U of epsilon Qn minus 1. You decompose the evolution into each term. Okay. So the Q and Qn are just dummy integrals. You integrate over. But to each configuration of that, you can associate to each Qi. So each choice of Qi, you can represent it by a kind of classical history. And use the fact that now you should use an explicit representation for the evolution operator at short times. Because if the time evolution is short enough, well, that's an unwavering argument, but it can be made rigorous. If the time evolution is small enough, the particles have a very low probability of going from to a point which is very far apart, because there is a conciliation of probabilities of the interference between probabilities. So basically, all what counts are the difference between a given point qi and a point qi plus 1 when the points are not far apart. So, and the final result is that if I write this evolution operator u, so if I write qi plus 1 times u of epsilon times qi, this is approximately 2I h bar epsilon divided by m to the power minus 1/2 times exponential of I over h bar m over 2 times qi plus 1 minus qi squared divided by epsilon minus epsilon, and you can write this as v of qi plus 1 plus v of qi divided by 2 plus higher order terms which are of order epsilon squared, basically. Okay. And so this is an expression when epsilon is small. Okay. And this is an expression which, in fact, becomes exact. So this is an approximate expression, but this becomes exact when v of qi is constant. Because then you can just solve the Schrödinger equation for a free particle, which is described by plane waves. That's an exercise. Okay. So the difficult part of the argument is to show that the results which is exact, so you do not have such a term where V do not depend on Q, remains valid when the potentials varies but is regular enough if V of Q, the potential, is regular enough. And I'm not going to describe mathematically what it is, but basically if it's a polynomial or a differentiable function up to some point, it works. Yes?
When we sum over all the histories, it means that you consider all the trajectories to be equally likely, but it sometimes can be that not all trajectories. Yeah.
No, here the trajectories are equally likely, but they get a phase because their action associated to each trajectory is different. Okay, and so there is a phase, and so there will be interferences between the trajectories. Okay, and as it happens, in fact, most of the contribution, most of the phase of the trajectory interfere in a destructive way. And I'm going to discuss that a bit later. Okay. And so, once you have that, you see, you have exponential of a phase, and you can check that this is just, basically, this term is up to term of order over epsilon squared. This is the classical action of the trajectory between point I and I plus 1, because it's epsilon times qi plus 1 minus qi divided by epsilon squared. So I can rewrite this as m epsilon times epsilon squared. And here I have an epsilon. So the epsilon, if you prefer, gets in front of everything. This is the square of a velocity for a trajectory that is linear. And this is the average potential, let's say, which is viewed by the particle when it moves from qi to qi plus 1. So you see. And this factor, you can put it in the measure. So basically, you can define a measure which is just a product from I equal 1 to n minus 1 of dqi with a factor which is complex to I bar h epsilon divided by m to the power minus 1, which is a discrete, which is a measure over discrete trajectories. That's a product of all these terms. So this is a measure over discrete trajectories. So a discrete trajectory is just a set of qi's, you see. So a discrete trajectory q is just a set of qi from I equals 0 to n, with the constraint that q0 is q initial and qn is q final. Okay, so you don't integrate over q initial and q final because they are fixed. Okay, and the product of exponential, so the products which now, the products come over intervals. So there are n intervals from qi equal, let's say 0 to n minus 1 of exponential of minus of I epsilon divided by h bar times this factor is just the exponential of I over h bar integral from 0 to t, while q initial is 0 and q final is q. I'm sorry. Yeah, t initial is 0 and t final is t. This is notation of dt m over 2 q dot squared minus v of q of t for such discrete piecewise linear trajectory. Well, up to term of order epsilon squared. And term of order exponent gives 1 plus term of order epsilon squared term when you sum them, that becomes term of order epsilon. Okay. And therefore, when you take the limit of this, you get this formula. So you can take the limit when epsilon goes to 0, which is called the continuous time limit. And in this limit, the path integral formula becomes exact. Okay. So for a general potential, it's not an exact formula if you use the finite discretized trajectory, if you discretize time, but when you take the continuum time limit, it becomes an exact formula. That's the beauty of the formalism. Yes? Yes?
When we construct the measure, we also included trajectories which jump from point to point faster than the speed of light. So how does it turn out that the path integral obeys relativity?
This is a formula for quantum mechanics, for a non-relativistic particle. So for such a system, the speed of light is infinite. So there is no contradiction, no paradox. And it's known that in a quantum field theory, this is more complicated because, indeed, if this was a relativistic particle, this formula will be modified because the propagator is not the same. But when you want to define a propagator for a quantum field theory, and in fact you defined it, I think you studied it in QFT1. If you want to view some amplitude of probability of creating a particle at some point and with some energy and absorbing it later at some other point, indeed such trajectory occurs. But then you have trajectories that goes faster than light, but these trajectories are very energetic. So you must take into account also the fact that you can create and absorb particles out of the vacuum. So even in a free theory, you have a trajectory particle like that, but some pairs of particles and antiparticles may appear and interfere with those ones. And at the end, for the physical amplitudes, there is no contradiction. Causality is respected. But that's something I think you have studied with Tibra, I think, and done. But you did the non-relativity case. So I think the consideration, when you studied the causality property of the two-point function in a free field, this is precisely the conditions that are satisfied so that there is no violation of causality and no faster than light propagation of physical effects. And when I'm going to compute the similar quantities in the path integral methods, which we'll be doing in 2 or 3 lectures, well, perhaps tomorrow, or rather on Wednesday, you'll see the same phenomenon. But here, this is non-relativistic, so the speed of light is infinite in this approximation. Okay. Yes?
So it's about maybe some physical interpretation
Yes.
of this calculation. So for each path,
Yes.
possible story, we're multiplying by
Yes.
some phase,
Yes.
and that will produce interference.
Yes.
And let's say that we have a really optimistic person that's saying, oh, so we're going to have a lot of interference, a lot of constructive interference.
Yes.
And then we have a pessimistic person that says, yeah, but if we are summing over all histories, we are going to have a lot of destructive interference.
Yes.
But actually, what happens is it's like a mix of both.
Yes, exactly. You are perfectly
At
right.
the end, what is left?
Okay, I'm going to discuss that a bit later, but I can give an answer, and that's one of the beauty of this formalism. In this formalism, it appears that basically in this formulation, when you have t time and q, and you want to compute the probability amplitudes to have propagate from this position to this position, so you have many. So you have trajectories that like that, and you have many trajectory. It turns out that the trajectories that are close to the classical trajectory interfere constructively. And those which are far destructively. Okay? And that's something which is called, that comes out from a mathematical theory of estimating what is the contribution, most important contribution in integrals like that, which is called the saddle point approximation, or the, stationary phase. It comes out from that. It's called the stationary phase approximation, which is a version of the saddle point method. Okay, so one of the beauty that was discovered and stressed by Feynman of this formalism is that you see the emergence of classical trajectory out of a purely quantum formulation of function. So you started from a quantum Hamiltonian, and the classical action for classical trajectory emerged from the existence of a quantum system with an Hamiltonian. That's it. That's not all the story about how classical mechanics emerged from quantum mechanics, because there is also decoherence and this kind of phenomenon you have studied. But that's the first step in the right direction. Yes?
And is this approximation always valid?
No. It's valid, basically, we're going to discuss that later. So it's valid, you see, in such a term like that. So this is middle. Okay. So basically, let me rewrite this result because it's important. So this result is that this propagator, Q final U of t dq initial given by first integral of dq exponential of I over h bar, the action of this classical trajectory. You see, you have two quantities here. You have the action for trajectory that are close to the classical trajectory, and you have h bar. And both are dimensionful numbers. Action is an energy times a time, and h bar has also dimension. So in fact, what's important is whether S for a classical trajectory divided by h bar is much larger than 1 or typically over the 1. If it's much larger than 1, then you see this is a big number. So as soon as this is not stationary, you have variation very big and destructive interference. If this is over the 1, then trajectories that are quite far apart from classical trajectory still interfere in a semi-constructive and destructive way. So this approximation is valid if this is larger than 1. Yes. A very nice example, if consider an atom with a nucleus and an electron. So and imagine that you have an electron that is very far apart, so almost on the verge of ionization. So such state, so this is an atom in what is called the Rydberg state. You see, you have one electron that is at very high, with orbital number very high. Okay. L is very large. For such a state, the action, the classical action of an electron, E minus, along a period is very big compared to h bar. So for such Rydberg space, the description of the state for this electron in terms of a classical trajectory, a Bohr orbit with just quantization of the action, is very good. You see, so Rydberg state is a good semi-classical picture. So basically, you have the classical picture. You have an atoms with electrons going out. Now, so here is a Rydberg space. L is very large. Okay, but for the low energy level, if L is over the 1, if L is 0, 1, 2, okay, then this is not true. So you need to know what is the wave function. You need to solve the Schrödinger equation to know what the structure, what the electronic structure, the electronic structure of the atom is, what are its ionization level. So here it's good, and here it's in general not good, except in some very, very special case. Well, basically, except for the hydrogen atom, the semi-classical picture breaks down when you go to low energy atoms. And for the hydrogen atom, it's continue because the hydrogen atom has a very special additional symmetry. It's an integrable system.
So when we quantize the state of this electron, yes, we cannot use Feynman integral approach.
It's not the best way. Yeah, no. It's not the best. You can do that, but it's as complicated as solving the Schrödinger equation.
So we use instead canonical quantization.
Yes, yes. So Feynman-Pals integral is good for some problems. It's bad for some other one. And Schrödinger equation is good for some problems. Simple system where you can solve it, that's okay. But for a complicated system with many degrees of freedom, for a system of an electron in a very complicated potential, chaotic or something like that, then semi-classical method may be better than solving by brute force the Schrödinger equation. Yes?
I have a little question. question. So you're saying that if the classical action is big, then the variation of the classical action is big, and the other way around.
Yeah, usually, yes.
But why would the variation of a number be big if the number is big?
Okay, I think I better discuss that tomorrow. I'll show you on an explicit calculation. Okay.
Question.
Yes?
And how does the pattern figure play when you allow observers? So you have an observer that can determine which trajectory the particle to.
Yes?
Then do you have to necessarily sum over the other parts in the
I'm sorry, I'm not sure I understood your question.
So let's say you have an initial position,
Yes.
a final position, and you are saying that you have summing over all
Yes.
possible paths. But what if maybe you know that it's not all the paths that need to be considered
Yes.
in the summation. You want to consider maybe a finite set of them.
Yes.
And would you still necessarily have the amplitude that you like get? For instance, would it be an integral or a summation? If it is not,
I'm not sure I completely. Can we discuss that after the course? Because I'm not sure I completely understood what you mean, and that's my fault. My hearing is not perfect, and therefore okay, better to ask, and I can come back to that for every one of us Okay, I'm sorry. Okay. Okay, so I still have a few minutes. So this is basically the idea. So I just discussed what you have seen already. But I want now to discuss something important related to both path integrals and methods and canonical formalism, which is that both canonical quantization and path integrals may be used to define something which is a bit fancy, which is called quantum mechanics at imaginary time, which is called Euclidean time too. Okay, so I'm going to do some formal math that probably some of you have already met, and then I'll discuss why it's interesting physically. Okay. So we have seen that the evolution operator U of t is exponential t over I h bar times the Hamiltonian, you see? And in general, for a system like, for instance, an harmonic oscillator in a potential V, H has a discrete spectrum. Well, it may have a continuum spectrum if there is some infinite space, but basically the important point is that H is bounded from below the spectrum. So we have the spectrum. So let's say that the state H applies to state I is EI times I. So this is spectrum of energy eigenstate with, of course, the energy of the ground state less than E1, less than E2, etc., up to possibly infinity. Okay, and I'm considering a very simple system where there are no symmetries, there are no degenerate states, but this applies. Okay, so spectrum for a very simple, ideal, simple system, like the harmonic oscillator, for instance. And you see that, of course, for t is a parameter in this definition. So, if t is real, u of t is unitary. So it means its eigenvalues are just pure phase. But now you may be interested in what's happening when t is complex. Because as a mathematical object, this is object. And you realize that because of this condition of the spectrum, u of t is what's called a bounded operator if the imaginary part of time of t is negative or 0. And by bounded operator, an operator A is bounded if if I consider a state, I apply A times A dagger times psi, because A doesn't need to be Hermitian. And if I define this by the square of the state, it is always bounded by some number which is called the norm squared of the operator, finite. This is called, for all, so let's say, the maximum, the sup of all states of this object, if it is finite, is called the square of the norm of the operator. So basically, A is basically the norm of the largest eigenvalues. Eigenvalue of the operator. It's a bit more complicated for infinite dimensional operator, but basically this corresponds to this. So an operator is bounded if this is finite. And you see that for this operator, if T has a negative imaginary part, you get an exponential of minus the absolute value of the imaginary part times a series of numbers that decreases. You see? So you can, in some sense, you can just diagonalize that by writing U of T as sum over the eigensystem of the projector on the eigenstate times exponential T over I h bar EI. This EI increases. So if this contains a negative real part, this coefficient goes to 0. So this is the real part. Well, I'm sorry, it's the modulus of E tie over I h bar EI goes to 0. Well, let's write this n, because otherwise we have 2 I goes to 0 as n goes to infinity if m of t is negative. Okay. And, well, bounded operators are something very important. Of course, well, lots of physical operators like position operators, momentum operators, the Hamiltonian, are not bounded. But for instance, if you are interested in a quantum information system where you have finite dimensional systems, all operators are matrices, so they are bounded. But nevertheless, bounded operators are important in the mathematical theory of quantum mechanics. And one reason is that bounded operators are basically the basics to define what is now called the theory of C-star algebras. That's a mathematical theory that is at the basis of the theory of operator algebra that is used to do quantum physics in a mathematical consistent framework. Okay. And for good reason. Okay. And one of the inventors of this formalism, it was not called C-star algebra at that time, but was John von Neumann, and he started all this business because one of his reasons why to give a proper formulation of quantum mechanics that would satisfy him mathematically, because he was a mathematician. Well, he was also a physicist, but he was one of the greatest mathematicians of. Okay, so bounded operators are very important, and you see that this is defined. So basically, you see that now we start from an object that depends on a time, which is a real. So this is the real axis. This is physical time. And we just make an analytic continuation of this object, a mathematical continuation of these two imaginary time. And you see that this is well defined in the lower half plane. U of t as a mathematical object, it doesn't describe anymore evolution of the system because it's not a unitary operator anymore. It's well defined here. U of t as a is bounded here. So as a mathematical object, it's something which is well defined. Okay. And moreover, there is one very interesting region, which is what's happening when t is imaginary, purely imaginary. So when t is real, this is the physical time. Now imagine that t is imaginary. So I'm going to write t as minus I times tau, where tau is positive, okay? And it's just a number, a positive number. Positive number. Okay. And then what does u of t becomes in this case? So u of t, of course, becomes, it's just exponential of minus I tau divided by I h bar, so minus tau divided by h bar h. So it's self-adjoint operator. Okay? And moreover, it's the exponential of minus some number times the Hamiltonian. So I think this should remind you of the density matrix of the quantum system at thermal equilibrium. Because if you consider your particle in your system, and you imagine now that it is in contact with a very big thermostat, so that it can exchange energy and become entangled with the thermostat. So now we have this system with our particles. We have a very big thermostat with temperature T. Capital T is the temperature. It becomes entangled. It exchanges energy. But when you consider what is the reduced density matrix, okay, as it was defined first, I think, by von Neumann and also by Landau and possibly by Bloch, I think, at the end of the, when around 2730. The reduced density matrix, when it's at thermal equilibrium, is just rho equal the normalized, so 1 over z times exponential of minus beta h, where h is the Hamiltonian, and beta is Boltzmann constant, so it's 1 over kb times t, where t is the temperature. And z is a partition function. So this is a reduced density matrix, and z, which is just trace of exponential of minus beta times the Hamiltonian. So this is an operator, so we have to take the trace. This is a partition function. Okay. And you see that this object has exactly the same form than this one. So basically, you have an analogy between tau divided by h bar and beta equal 1 over Boltzmann constant times the temperature. So it's a mathematical analogy, but it's a very, very deep analogy. You see, you may think of imaginary time along the negative real axis for the imaginary part has some kind of inverse of temperature. Okay? And let me end up with just a few things. No, this is real. So with this analogy in mind, tau, which is, so I wrote t equal minus I tau, so tau is I real time, is called often Euclidean time. And that's a very useful analogy. Why is it called Euclidean? That's because, well, let's forget that our system is a non-relativistic system, and just let's go back to well, standard special relativity. When I state C equal 1 and h bar equal 1 if I'm doing quantum mechanics. And so the line element in Minkowski space is ds squared equal minus dt squared plus dx squared, where I'm using this choice of signature, which is called, I think, the East Coast signature, because it is used by Weinberg and people in this part of North America. And of course, it's the opposite of the signature that you have been using as far as in the QFT1 course, because I think one of the reasons is that you relied on the excellent book by Peskin and Schroeder, and they live in the West Coast. So this is opposite to the plus, minus, 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 which is the West.
Which one do you prefer?
I'm used. It's a matter of, well, I'm used to this one because I've been doing a lot of things in statistical mechanics where this one is more convenient. But well, it's a good exercise to keep one's mind flexible to switch from one to another one. And I don't know if there is a grid plane signature, but no, we'll see. Okay, so if I am using this one, which is a Minkowski space, so ds squared here is when it's real, we have a space-like vector, and when it's negative, we have a time-like vector. Okay, if you make this transformation, this rotation, this becomes d squared equal d tau squared plus dx squared, which is Euclidean metric. Okay, so this is a very trivial remark, but it's going to play an important role in the rest of the lecture. And so you see that if you make this transformation, the metric of a space-time with imaginary time becomes just an Euclidean space-time. Okay, hence the name. And this transformation, that going from real time to imaginary time, you do that by performing a rotation by a factor e I pi minus I pi over 2. It's called a Wick rotation. This means a rotation in the complex plane of time. Okay. Okay, and well, if I have just 1 minute left, let me see that. Well, I think we can see that later, but you see that the partition function is just given by, with this notation, the partition function for a system at temperature T is just the trace of U of minus I tau with tau equal h bar over Boltzmann times the temperature. Okay. So it's the partition function of a system at temperature T is just the trace of the evolution operator at imaginary time. So for this reason, this U of minus I tau is, I'm going to denote that, the Euclidean evolution operator. It's not an evolution operator anymore because it's not unitary, but just and denoted by UE with E for Euclidean. So here, Euclidean and tau is a real variable, but when you, so here UE is well defined, is unitary. I'm sorry, is Hermitian. So on this line, UE is self-adjoint. And on these lines, U is unitary. Okay, are the same object. Okay, so this is trace of UE of tau. Okay, so this is just, I made a dictionary. Okay, but you see that what's important is this relation. You can view Euclidean time as the inverse of a temperature. Okay, and next, well, tomorrow I'm going to show you that this path integral formulation can easily be generalized to a path integral representation for this unitary with this Euclidean evolution operator, and this is going to make a contact with statistical mechanics, model of statistical mechanics, and to make to give a nice physical interpretation of this temperature of the quantum system in terms of number of degrees of freedom of a classical statistical mechanical system. But that's for tomorrow. Okay. Thank you. Okay. Any question? Yes?
And this relationship between the matter time and the temperature, does it hint of a possible relationship between entropy and time as well? Because the way entropy doesn't decrease and time also doesn't go back, perhaps it can be a thing.
Can you speak a bit louder? I'm sorry.
And the relationship you were able to draw between the imaginary time and temperature.
Yes.
Can it possibly hint of a relationship between the entropy and temperature and time as well?
I don't think in these formulations there is a direct relation. Well, of course, since you have a partition function for something that I'm going to, you can define the entropy in the usual way. And for this system at finite temperature, the entropy you'll get will be the von Neumann entropy, I think. So for this quantum, so this is a partition function for, so this Z is a partition function for a quantum system. Okay? And therefore I think you just apply the rules of thermodynamics and you get an entropy. It's going just to be the von Neumann entropy for this Gibbs state. You know that the entropy for the quantum statistical system is just a special case of the von Neumann entropy. So you can view it as the entanglement entropy of the system with respect to the thermostat, or just as the thermodynamical entropy, but that's the same. That's the same thing. And S is, if I'm not mistaken, just minus the trace of whole ago. Minus of what? There is a KB factor. With rho given by this. But it's just, well, it's an exercise. Quantum statistical mechanics, or statistical mechanics. Okay.
Do you think can you use this to explain why time does not move backwards?
Pardon?
Why time
Yes.
doesn't move backwards, but always forward, always increases, because entropy always increases. I can't decrease.
Well, in this definition, of course, the orientation of time is important. If you want to, if time runs backwards, what you are considering is u of minus t. So you are considering the conjugate of the evolution operator, u minus 1 of t, or u dagger of t. So of course, this is well defined. If you start from a negative time to go there, you have to do, if you want, an anti-Wick rotation. Because if you make the Wick rotation here, you go to a region where U as a mathematical bounded operator is not well defined. So you have to be careful. Going from there, from real time to imaginary time, you have to take into account whether time is positive or negative. So it's related to causality. But everything is consistent. Okay? But I'm going to discuss that a bit more tomorrow. So you'll see that both make sense. Time in this direction and time in this direction makes sense. And it's possibly related to something you have seen already in statistical mechanics, or something that definitely you are going to see in condensed matter. I think it's called the Schwinger-Keldysh formalism for quantum statistical mechanics.